Good morning. Wait a few more seconds for people to sit down. Right, so good morning. It's a pleasure today to have, for this IAP colloquium, we have Danielle Leonard, who was a PhD student at the University of Oxford, graduated in 2016, postdoctoral fellow at Carnegie Mellon University in Pittsburgh in the USA, and since 2019 has been a lecturer at the University of Newcastle. Danielle has several leadership roles in the LSST desk collaboration, and that is why actually we wanted to have her speak here. LSST desk, as you know, is this collaboration in charge of analysis of the Rubin Observatory data. And in particular, Danielle has expertise in weak gravitational lensing, in particular lensing tests of gravity and intrinsic alignments of galaxies. So this is actually going to be the subject of today's colloquium. Thank you for being here.
Okay. Bon, alors, bonjour à tous et merci bien pour m'avoir invité. Je suis heureuse d'être ici et d'avoir l'opportunité de visiter Paris pour la première fois en 8 ans. And okay, so thank you very much. I will switch back to English now, but si vous voulez me parler en français plus tard, ça va. So thank you, and thank you to Florent for the invitation. I'm really excited to be here. I've been to the IAP once 8 years ago, but this is my first time back, and first time back in Paris for 8 years, one pandemic later. So today I'm going to be talking about mostly to do with what Florent said, so measuring and modeling the intrinsic alignment of galaxies in the context of weak lensing. So, and I know we have quite a broad audience subject-wise, so we'll have a nice introduction, hopefully, to weak lensing to start. And then we'll talk more specifically about intrinsic alignment. So to begin, though, I want to just share a little bit about more broadly what I work on. So if anybody would like to talk to me about more general aspects of my work later that we don't cover today. And I wanted to also show the students who are working with me, in case you come across them, then you know a little bit about what they're doing. So most of what I work on, well, all of what I work on, I would say, is related to late time observational cosmology, specifically weak lensing and galaxy clustering, focusing on photometric or imaging surveys. And that kind of falls under two realms. So one of which is what I'll be speaking about today, which is modeling astrophysical effects that impact cosmological measurements. So things like the intrinsic alignment of galaxies affecting the weak lensing measurements we want to make and needing to account for that. Understanding how different astrophysical effects can have similar impacts on our cosmological measurements and how we account for that in the modeling. And also lately working a little bit on how we can use emulators effectively to speed up our analyses. So I know that may be of interest to some people here. And so I have 3 PhD students, Carolyn, Charlie, and Nico, who are working in this area. And I'll reference them later when we talk about work relevant to what they have been working on with me. And then I'm also interested in constraining extended models of cosmology. So related to alternative theories of gravity mostly, but mostly I'm interested in, are we okay? Okay. Mostly I'm interested in understanding how we can take advantage of as much data as possible when we're doing tests of alternative cosmological models that alter the structure formation that we expect on scales where linear perturbation theory no longer applies. So I have one PhD student, Carola, who is working on this. And if you're interested in alternative theories of gravity, please do feel free to talk to me about that later. I'm here for the rest of today. So to get into the subject of the talk, so I guess for some of you, this will be pretty well-known lore, but just to recap. So in cosmology, we have a problem at the moment. We have a couple problems. And that is to do with the fact that we want to describe our universe and its evolution and its composition using a limited number of parameters in our standard cosmological model. We have typically 5 or 6, depending on if you allow curvature parameters in our standard cosmological model. And we would ideally, if our model is correct, expect to measure the same values of these parameters from all our observations. But what we are finding in recent years is that for at least a couple of these parameters, this is not necessarily the case. And so probably many of you will be familiar with the idea of the Hubble parameter tension, where we see differences from cosmic microwave background inference of the Hubble constant versus the supernova measurements of the Hubble constant at 5 sigma, so pretty severe. The other one that's more relevant for the types of observations I'll be talking about today is the tension in either what we might call the sigma 8 parameter, or you might call the S8 parameter, which is a combination of sigma 8 and another parameter omega m. And basically you can think about this as being related to the amplitude of the fluctuations in the matter field. And this, we also see a discrepancy between, well, it depends, you can define it different ways and you can split things up different ways, but largely you could talk about this as being related to a discrepancy between what we measure for this from the cosmic microwave background and from later time observables like weak lensing and galaxy clustering. And this discrepancy isn't quite as bad as the Hubble constant tension. It's more like 2 or 3 sigma. But it is sort of persistent. And we are interested in figuring out what's going on here, because if it is real, if either of these are real, it points to the idea that our standard cosmological model, so lambda CDM, where we have a dark energy that's constant and we have whole dark matter, is lacking something if it is real. Now, it may not be a result of this. It could be a result of systematic effects. So this is part of the motivation for what we're worrying about today in terms of intrinsic alignments and making sure we get this kind of modeling right. But like I said, so that's the sort of broad context. The specific kinds of measurements I'm going to talk about mostly today are to do with weak gravitational lensing. And so I want to give a brief background on that. This is a lovely illustration that I did not create. This is due to Jessie Muir, who is a postdoctoral fellow at Perimeter Institute, who is working in the Dark Energy Survey, and she made this series of great illustrations, but I will use it to describe weak lensing. So the idea of gravitational lensing is that we have sources of light far away from us along the line of sight, and their light travels to us through the intervening universe. So in this case, this is going to be the sort of yellow galaxies. I was told there's a big stick, so perhaps I will use it now. This is going to be the sort of yellow galaxies illustrated in the back here. And the light is going to travel towards the observer. But as we see, it's not traveling in a vacuum. It's going to pass by other structures. So this is going to be other dark matter structures, structures that contain galaxies as well. And the light that's coming from the background galaxies is going to be deflected by the mass that exists between the background galaxies and the observer. And this is a general relativistic effect. And because of this deflection, we don't see the background galaxies as we would if that light was just moving in a vacuum. We see the background galaxies distorted. And so what we see here in the blue box is what the galaxies might look like in a vacuum. But in the yellow box is what we actually see. And so what we see is that the galaxy shapes change. Obviously, this is wildly exaggerated and also a cartoon. But we see the galaxy shapes become more elongated. So this is one key feature that we're going to take advantage of. The ellipticity changes. We also see that the galaxies are tending to align in their sort of distorted images to be tangential around the foreground matter. So that's a typical situation. And another thing that we're not seeing so much here, but that does exist, is that the brightness of the background galaxies as we perceive it will change. And so we typically try to measure this kind of effect by measuring correlations in the shapes of the background galaxies. This is, like I said, exaggerated. For weak gravitational lensing, we would be trying to measure distortions that were on the level of percents, so small enough that we would not necessarily be able to distinguish it obviously just visually. So this is the effect that we're going after. So this is again due to Jesse, this illustration. It's a very nice illustration. So specifically the way that we go about this, kind of trying to capture this effect and measure it, is that, well, we do this in a bunch of different ways, but the way that I'll be talking about today is by measuring 2-point functions related to weak lensing. So what is this? So there's a few different types of 2-point functions we might measure. So here we have on the top panel a illustration of a telescope, which is, observing 2 different samples of galaxies. So we're illustrating that we have these yellow galaxies, which are largely further in the background, and red galaxies, which are largely further in the foreground. These are not astrophysical colors. These are just illustrative colors. And so what we should think about the yellow galaxies as being what we call our source sample. So these are the galaxies where what we are concerned with is the light that is coming from them being distorted. We are treating them as light sources only. And what we care about is how their shapes are changing due to distortion. We also have the red galaxies, and these ones, we are treating them as tracers of the structure that exists between the sources and the observer. So these are more what we care about. What we care about for these galaxies is more their positions, because what we're using them to do is trace the dark matter structure that is causing the lensing. And so what we want to do here is extract the signal of the lensing, right? So there's a few different ways you could do this. And the main idea is that you imagine that this lensing effect is going to imprint correlations between different galaxies. So if I think about taking, for example, it's probably actually easiest to think about clustering first. So this actually would only be considering the red galaxies. So this is actually not a lensing effect at all. And I realize now as I'm saying this is actually probably a confusing way to explain this. So I'm sorry. We're now briefly ignoring the lensing effect and considering only the red galaxies, which we're using to trace the dark matter structure. And what we're doing here is we're saying, if I have a galaxy at a given position, so I'll use my big stick again. If I have a galaxy at a given position here, what I want to know is what is the excess probability above random of having another galaxy at a certain separation, which is being indicated as different separations by these white lines. And so the reason that you would, of course, have an excess probability above random is because you have these galaxies tracing the dark matter structure, which is there because of gravity and other effects like baryonic physics at small scales. So you have correlations in the positions, and this is one type of 2-point function. So it's 2 points because you're getting the correlation between 2 points, right? The next thing you might try to measure is, okay, let's say instead of considering one galaxy here, and I think about the position of another galaxy here, I say I consider one of my red foreground galaxies, and I ask, what is the excess probability of having a galaxy from the background sample with a certain ellipticity relative to the foreground galaxy at a certain separation? So this is capturing that tangential effect that we just saw on the previous slide. So we are more likely to have galaxies in the background distribution that are tangentially oriented around galaxies in the foreground distribution because of the lensing effect. And this is as a function of the separation between galaxies. Okay, and then we can go to the third option, which is that you say, if I have a galaxy with a certain ellipticity relative to some coordinate system here in the background sample, and I have another galaxy at a certain angular separation from that galaxy with a certain ellipticity, there's going to be correlations in the ellipticities that these galaxies have, which is dependent on their separation. And that's going to be due to the fact that light from a background galaxy that's here is going to pass through similar dark matter structure as light from a background galaxy that's close to it. So we're capturing this information about correlations, which if you're noticing what I'm saying, right, and for some of you this will be very familiar, but if you're noticing what I'm saying and this is not so familiar to you, all of these correlations are due to either the dark matter structure that the light is passing through, or something to do with the propagation of light. That's the other option. But mostly it's due to the dark matter structure. So we're really using this effect, the lensing, and also just the clustering of the foreground galaxies to learn something about the dark matter structure in projection. And that's going to translate to learning something about our cosmological model. So that's sort of the basic idea for the type of weak lensing and clustering statistics that we're talking about today. There's a little bit of a subtlety in that what we often do is that we, in fact, don't just have two samples, but we take our yellow galaxies and our red galaxies and we separate those into redshift bins. And we don't have good redshifts for these most of the time. So like I said, this is imaging data only most of the time. And so we have photometric redshifts, which means that we have some uncertainty in our redshifts that's pretty significant at times, but we separate these into redshift bins and we consider correlations between all of the redshift bins. And so when you do that, you end up with a sort of data set that can be summarized in measurements that look like something like this. So here we have the case where you're correlating the foreground galaxy, the red galaxies on the previous slide, and the background shape of the yellow galaxy. So galaxy, what we call galaxy-galaxy lensing, so the shape cross-position 2-point. This is for the dark energy survey, which is one of the sort of currently analyzing the data surveys, stage 3 surveys. And what we have here in this grid is the cross correlations between the redshift bins. So I said we have these redshift bins for each of the foreground red galaxies and the background sources. And we can cross correlate between all those bins. And that's what each of the little squares are. But then we have also within the square, we have a data vector as a function of the angular separation. So that's what the data vector actually looks like. The points here are the measurements with error bars. The lines are the best fit model for the standard cosmological model, lambda CDM. Right, so, what actually goes into calculating the model is part of what we're interested in here. And like I said, it's related to, we calculate the model by calculating things to do with the structure. So we care about our cosmological model because that's going to tell us about things like what is the fractional density of dark matter in the universe? What is the fractional density of baryonic matter? What is the fractional density of dark energy? How big are the fluctuations in the early universe that lead us to having structure in the late universe? Those are the kinds of things that go into the cosmological parameters. But to calculate this model, we also have to consider anything else that could be going into our measurements that's not those cosmological effects. So we have usually about 20 to 30 further parameters that describe other effects. So this is both astrophysical, which is what I will focus on and what I'm interested in mostly, but also measurement effects, so measurement calibration. So there's actually usually sort of 20 to 30 total, well, more than 30 in some cases, total parameters that we have to deal with here in getting a best fit model. And so as Florent said at the beginning, this is the context. And I mean, I think most of you here especially who maybe work on cosmology will be extremely familiar with the picture of the launch of Euclid, because I think there's a lot of Euclid folks here. And so we kind of have, we're at a point right now where we have a couple of surveys that are coming up very soon, which are going to be extremely exciting for this field. So the figure here, not the picture, the plot, is showing surveys that at different stages, indicated by different colors. So the blue dots are surveys that have been completed. The purple dots are surveys that are either ongoing or the analysis is ongoing. And so we would call those, the nomenclature we use is that these are stage 3 lensing surveys. And the green dots are Euclid and LSST, and these are stage 4. There's also Rubin, which is a US space-based mission. It's a little bit further down the line, but that would also be stage 4. It's just not on this plot. And what we're plotting here is the galaxies per square arc minute expected from these surveys and the area of these surveys. Because the thing we really care about in cosmology, as we were talking about with some of the PhD students earlier, is in terms of reducing our errors, is really numbers. Because what we're really doing is getting a expectation value for a signal that we care about. And the way that we measure that more precisely is we get more, in this case, pairs of galaxies to put into our 2-point function measurements. And what we see here is that Euclid and LSST are going to have more galaxies per square arc minute, meaning they go deeper. So that would be how you get more galaxies per square arc minute. And also much greater area than anything we've seen before. And so the statistical power of these surveys is very different than what we're used to dealing with. So as we see, obviously here, Euclid is space-based, LSST is ground-based. There's differences there that are very important in the kind of data that we end up getting. But we both surveys have this sort of paradigm of having much lower statistical uncertainty than we're used to. And so we need to make sure that, I mean, it would be a bit silly to do these like big surveys and end up being completely limited to the same precision as we had in stage 3, just by the fact that we don't have good enough models, for example, for all those other effects that go into our into our best fit models that we saw in the previous slide. So that's the context. We have to worry about modeling a lot of stuff that we didn't necessarily have to worry about modeling before. And just to emphasize that a bit more, here is some plots that are sort of hand wavy showing what the situation is for how we're going forward. So this is LSST focus because that's what I work on. But the statistical noise for LSST on weak lensing is for the first time, expected to be for the first time at a point where we can make some really exciting tests of the kinds of modified gravity theories that I mentioned before. And also to be able to say something a lot clearer, even with year 1 here on the left, about this sigma 8 tension. So we could see, you know, is it actually pushing to more than this 2 or 3 sigma that we're seeing at the moment? So that's just to kind of illustrate in a hand wavy way. But as I said, we do have to be very careful about these modeling uncertainties. And so the kinds of things that I'm interested in are, like I said, mostly to do with astrophysical effects that have to go into our modeling of our cosmological signal. There are lots of other things that we need to worry about, like detector effects, measurement biases, stuff like this, which are also very interesting and important to get right. But I will obviously be talking about the stuff that I work on. And so the kinds of things that I am interested in making sure that we are modeling to a high enough level of precision is to do with, for example, photometric redshift estimation. I would say that's like a little bit different than an astrophysical effect in the sense of the others, but I put it in there because it's, I guess, an astronomical effect in that we don't have spectra, like I said. And so this is kind of to illustrate, we would love it if the spectroscopic redshift and the photometric redshift of all of our galaxies was exactly the same. And these lines, we just had a 1-to-1 correspondence. But in fact, it's very, very difficult to get accurate photometric redshift estimations that don't bias the full distribution of your galaxies with redshift. And so what this means is that we have to be very careful about modeling the uncertainty that goes into the photometric redshift estimation. So that's not quite the same. That's not quite the type of astrophysical effect that the others are, but I'll lump it in there, like I said. The other three that I'll mention here are baryonic effects. So I always get kind of laughed at by my colleagues who work on AGN when I mention this, because basically I'm saying that the thing that they care about the most is a systematic error for me. But we're worried about the fact that if you have significant AGN feedback or winds, gas physics of various kinds that mean that at small scales, our uncertainty in how we model our summary statistics, our 2-point statistics for our dark matter is very uncertain. So this is an illustration on the bottom left here, where we have this is a 2-point statistic in Fourier space, where we have we've kind of normalized it out so that we see on the larger scales, so smaller k, because it's Fourier space, everything is kind of agreeing with each other. Whereas when we go to the smaller scales, so larger k, and we include these kind of effects with different viable models, there's a lot of disagreement. So if we can't control that uncertainty, we're going to be in trouble. Galaxy bias, that's to do with the fact that we don't have a perfect understanding of how the galaxies trace the dark matter. And then intrinsic alignment of galaxies, which is what I will focus on for the rest of the time. So to give a bit more of physics behind that, so what is the intrinsic alignment of galaxies? So I spent all this time talking to you about how if we make measurements of the correlations of shapes of background galaxies, this can tell us about the structure of dark matter along the line of sight, and that is due to the fact that those correlations are sourced by weak lensing. But unfortunately for us, they are not only sourced by weak lensing. So the intrinsic alignment of galaxies is the effect where, of course, if we think about it, galaxies are also going to have correlations in their shapes as a result of, for example, tidal effects. So you have, for example, two galaxies that are close enough to each other that they are physically, tidally stretched towards the same dark matter structure, or in the case of, for example, elliptical galaxies. Or you could also have correlations that would affect your 2-point weak lensing measurement. If you have a foreground galaxy that is tidally stretched towards a dark matter structure, and then you have a background galaxy that is actually being lensed by that dark matter structure. So both of these can contaminate our weak lensing measurement. I mean, we expect some of this correlation, this type of correlation, to be present when we do just measure these correlations in shapes. And we see, again, with my hand-waving plot, that this is a limiting systematic for LSST. If we don't get this under control, we will not be able to do the types of dark energy and modified gravity model testing that we would really like to do. So what can you do here, right? What you would like to do is measure separately the signal that is related to the intrinsic alignment, so the tidal alignment. Now, I should say it doesn't have to be just basic tidal physics. It could also be that intrinsic alignment is sourced by the sort of environmental effects related to the formation and assembly of galaxies and halos, depending on sort of the scales at which we're looking at. We have a fairly good understanding of the tidal physics that goes into the intrinsic alignment signal at relatively large galaxy separations between galaxies, so especially outside of a single halo, but not perfectly. We have a much less of an understanding of what happens at the smaller scales, where we expect there to be more effects from the galaxy history and the assembly history, the galaxy formation history and assembly history of galaxy groups. So yeah, to return to what I was saying, What we would really like is to get a better handle on this signal, because if we knew what we expect this signal, this contribution to these correlations from intrinsic alignment to look like, if we knew that precisely, then we can include it in our model, and we don't have this problem anymore, or we have it to a much lesser extent, depending how precisely we make this measurement. So that's our goal here, to separately measure the intrinsic alignment from the alignment due to the weak lensing. Now, there's a few ways you can think about doing that. So one is you get a subsample of your galaxies where you actually have spectroscopic redshifts. I don't know if I actually said the reason that we don't have spectroscopic redshift for weak lensing samples is because they are too big. So we're talking about hundreds of millions of galaxies, or even billions of galaxies that we expect for LSST. We can't get spectra for all of those. Too expensive. So you think about, okay, I have a subset of my galaxies where I have a spectrum. And what that allows me to do is say my galaxies are actually localized in 3D space. And then I can actually measure the signal to say, okay, I have a galaxy that I to another galaxy in redshift. And this means that there's no lensing correlation between the galaxy in the red sample from earlier and the galaxy in the yellow sample if they're at the same redshift, because the galaxy in the yellow sample, the source sample, would have to be further back to allow that to be lensed by the structure that the red sample galaxy is tracing. So if these two are at the same redshift, we know we've excluded the lensing effect and we can measure the intrinsic alignment. So that's a good idea, and people definitely do that. The problem with that is that spectra are expensive and they're more difficult to get for some galaxies than for others. So usually if you have a spectroscopic sample that is big enough to measure this kind of signal, it is going to be biased towards galaxies that are higher luminosity, for example, and potentially have a selection effect on the color of the galaxies, the real color, not the illustration color this time. And so what that means is that you measure an intrinsic alignment effect, and that is a useful tool for building models, but you measure it for a different sample than what you actually are looking at. So that's not necessarily the most useful. You can also imagine doing that same kind of game, right? And saying, I want to measure in the same, I want to measure in a bin. So I say I had these redshift bins earlier. I want to measure in a bin where my red galaxies, now we're talking about illustrations, and my red galaxies in the foreground and my yellow source galaxies, the bins are in the same redshift regime, right? So I don't expect much lensing there in those correlations. And so you can try to do that, but do it with photometric redshifts. You can try. There are some methods that advocate this. It's proving to not work very well, in my opinion and experience. So for example, this is trying to apply this to dark energy survey data with myself and some collaborators. And what we see is that we expect the intrinsic alignment signal, the sign of the intrinsic alignment signal here to be negative, and which is illustrated here by the hollow measurement point. We have one negative point, and the rest of it we have positive, which is physically not what we expect at all. And when we do a model that includes intrinsic alignment and a residual, which is due to photometric redshift uncertainty issues, we find that our signal is almost exclusively explained by photometric redshift uncertainties, and we're really hitting a floor here. So this doesn't seem to be working so well. There's similar techniques in what is called like a self-calibration technique for the experts in the room, I guess, who might be familiar with this. That also requires you to split your source sample using photometric redshifts. This is dicey. So I guess, how are we doing for time? 10 to 15 minutes. Okay, perfect. So I'll talk about another option now. So this is another way that you can try to get the signal that you want to measure the intrinsic alignment on the actual type of galaxies that you have in your weak lensing sample. So this is something that could solve this problem, right? So instead of trying to split your galaxies on redshift, and cancel, effectively null out the lensing correlation that way. We can notice that the intrinsic alignment effect and the lensing effect have a different impact on the actual galaxy images. So this is illustrative, but it is actually using a simulation code that is physically correct. It's just exaggerated. We have an original image of our nice elliptical galaxy. If we induce a lensing shear on that galaxy, so shear, I'm using shear to mean the change in the shape here, the change in the ellipticity, then it's going to look something like the middle image. If we induce an intrinsic alignment related change in the shape from a tidal effect, it's going to look something like the bottom image. And the difference that I'm just going to discuss exploiting here is the fact that lensing is really to do with the light, right, that's emitted from the galaxy. So when you measure a distortion in the shape of the galaxy due to lensing, the effect on the change in the galaxy's measured ellipticity is the same no matter which sort of isophote of the light profile at which you measure that ellipticity. So we have a symmetry in the lensing shift to the shear, regardless of whether my tool for estimating that ellipticity is sensitive to the inner, sensitive to the inner region of the galaxy versus the outer region of the galaxy. Intrinsic alignment, on the other hand, this is not the case because it is a physical effect that has a greater impact at the outer regions of the galaxy. And so this has been shown to be the case observationally in a number of different works where you use different shape estimators that have different sensitivities to the different regions of the galaxy image. You get intrinsic alignment signals out that are different by a constant amplitude. And so you can exploit this. So if you use different shape estimators that are, sensitive to the inner part of your galaxy light profile, so here you get a smaller intrinsic alignment signal because as you can see, the ellipticity effect is less at the inner light profile. And if you use shape estimators that are sensitive to the outer part of your galaxy light profile, you will theoretically, and as is borne out, get a amplitude that is higher for your intrinsic alignment. But your lensing stays the same. So that's the key. So in 2018, myself and Rachel Mandelbaum proposed this as an idea to get at the IA signal. And that paper was sort of just, this is a nice idea. Maybe it would work. Here are some forecasts. Okay. More recently, my student, Charlie McMahon-Geller, and I were trying to see if this actually works in practice. Because obviously, best laid plans don't always work out. So what we did is we took advantage of the fact that the dark energy survey, so one of these current surveys, in year one provided multiple shape estimates for their main galaxy catalog. Now, these were not shape estimates that were specifically optimized for the type of measurement we're doing here. So they weren't necessarily, it wasn't that we had one that was really sensitive to the inner part of the galaxy light profile and one that was really sensitive to the outer part. We just kind of had what we had. And what we really wanted to see was just, could we make this work? And we did manage to make a measurement that we mostly trust. And by measurement, I mean a null measurement. We're consistent with 0. These data points are correlated, I will tell you. So it looks like, you may not think that is consistent with 0, but the data points are quite correlated, and it is. what we learned from the first process of applying this is that what we really need is to not be using shape estimates that are not optimized for this. So to not be trying to do this kind of measurement sort of a posteriori, given a set of catalog data. What we really need is to be working at the image level, and developing shape measurements that work for this method specifically. And that's going to allow us to not have issues correcting for our selection effects within the catalog, which is something we came across. And Charlie did a really interesting attempt at correcting this using machine learning algorithms to try to estimate the selection effect that was present. We can talk about that later if anybody's interested in that, but it was not perfect. We need a unified weighting scheme for our estimators. We didn't have a way of constructing that was unbiased given the data that we had available from Dark Energy Survey Year 1. And we found that we do need to worry a little bit about something called multiplicative bias, which is something that affects our weak lensing measurements. Now, in the original proposal here, we sort of presented the idea that you could do this kind of measurement of intrinsic alignment with shape estimators for galaxies that had demonstrably did not suffer from this systematic error, but this doesn't seem to be something that is going to be feasible for LSST. So we need to worry about multiplicative bias, which is basically to do with an error related to the actual measurement of the shapes from the images. So Charlie and I did some forecasts to see, like, would this actually be feasible for LSST with the multiplicative bias issues? And it does seem like it would be, but we do need to, so these two plots are showing two parameters of the pair of shape estimators that you need to use to get this to work. So the two things you need to worry about are essentially how similar are the intrinsic alignment amplitudes that you get out of your from your shape estimator. So this is a proxy for like what bit of the galaxy are you measuring? And also how correlated is what is called the shape noise, which is the Poisson-like noise for the two estimators. And so if you can tune these parameters correctly, you can get a pretty promising sinusoids of this type of measurement. However, you do have to be able to tune these parameters correctly. And so what we're looking at is using is now trying to sort of tune the parameters of a type of estimators, which some of you, I guess the experts in the room, may be familiar with, which is the FPFS or ANACAL type estimators, which are analytic shear estimators, which are very, very fast. They're very exciting because they're very, very fast. They can allow us to do multiple shear estimates on the same set of data in sort of almost trivial amounts of time, which is essential for this kind of method because we need multiple shear estimates to do this. And they have radial weightings, which on the galaxy image, which can be tuned directly. So we're working on this, but to be able to create these shear estimators and make sure they are sort of appropriate and do give us the kind of sensitivity to different parts of the galaxy light profile that we're interested in, we need simulated images that have this kind of radially dependent intrinsic alignment effect on it per galaxy image level. And these do not exist. So we have a precursor project at the moment, which is creating these simulations. This is a public code that's under development, which if any of you use the code GalSim, which does this kind of galaxy simulations for weak lensing, this is a plugin that we're developing, myself, Charlie, as well as Zhengcheng Li and Rachel Mandelbaum at CMU, to create image simulations suitable for weak lensing shear estimation tests, which do actually have this realistic, radially dependent intrinsic alignment signal. And so you can feel free to check out the GitHub repository if this is of interest to you, because I know that having non-affine effects. This is very technical, but non-affine effects on weak lensing images is also useful for other things, like, for example, if you're interested in measuring flexion, which is a high-order weak lensing effect. Okay. Timing-wise, 5 minutes. Okay. So I guess maybe very quickly, I'll move on to another aspect of, I'll have a quick summary of another aspect of intrinsic alignment mitigation that is potentially of interest. So something else, so that was to do with making measurements of the signal of intrinsic alignments on the specific data set that we're interested in, and being able to then precisely get that signal and include it in our modeling so that we're sure that we are not biasing our results by having an incorrect model for the intrinsic alignment signal. Something else that we would like to have available is not just the image simulations that I spoke about just now that have realistic intrinsic alignment effects, but we would like to have large-scale n-body and mock galaxy catalog simulations that include the correlations that I've been talking about that are due to intrinsic alignments and include those correctly. And this is sort of non-trivial. So ideally, you would do hydrodynamical simulations, and you would actually include, the tidal physics and the galaxy formation that would naturally have the intrinsic alignment effects sort of pop out. And people certainly do that to study intrinsic alignment in simulations. But the scale at which you can do a hydrodynamical simulation for that is not the same scale at which you might want to have n-body simulations to produce mock catalogs for the validation of sort of survey pipelines. So what we often do in that case, it's not just intrinsic alignments where this is an issue, is we have n-body simulations, so dark matter only, which are cheaper to run at these large scales. And then we populate the dark matter halos that show up there with galaxies, which are populated according to a halo occupation distribution, the parameters of which, so a recipe for how you put galaxies in these halos, the parameters of which are fit to, for example, a hydrodynamical simulation or observations. So that's how you usually do this. The issue is that those types of models don't include intrinsic alignments usually. So they're only to do with, do you have a halo, do you have a galaxy in this halo? What is the mass of that galaxy? What is the mass of the halo? Not to do with how is that galaxy oriented. So this is something where I'll just in the last couple of minutes mention, we've been working on trying to add as a functionality to this type of mock galaxy catalog creation. And so this is a project that was led by Nick Van Alphen, who's a PhD student in desk at Northeastern in the US. But essentially, we're talking about creating a halo occupation distribution type model. So a model that tells a recipe for where to put these galaxies in the n-body simulation halos that also accounts for the orientation. So we're talking about being able to orient for example, satellite galaxies in a halo appropriately with respect to either the a radial vector to the center of the halo, if we don't have subhalo information about the shapes, or if we do have subhalo information, shape information for a subhalo, which we don't always have, but if we do, actually orienting a satellite galaxy with respect to the subhalo as well. And so we do this by having a simple additional parameter that describes the misalignment of the satellite galaxy with respect to either one of those vectors. And we're able to reproduce alignment correlations from hydrodynamical simulations pretty well. So that's sort of a nice success of that method. There are still some issues. What we're seeing is, and I won't go into this in detail, but I would say maybe is it an issue, is it a feature, or is it a bug? Unclear. What we're seeing is indications that that support the idea that you have to worry about if you care about satellite galaxy alignments with other outside of halo structures, you will not get that correct from this method. And so what that could be considered like there's something wrong with the method, but it's also telling us that satellite galaxies seem to care about alignment that is not sourced only from within their own halo, which is kind of interesting, right? It could tell you something about what you expect in terms of the when the alignment is imprinted, whether it's due to formation history prior to assembly within a halo or something like this. I won't go into details about that, but it's an interesting topic for further exploration. Obviously, I don't have time to talk about this, but if anyone would like to talk to me later about photometric redshifts and intrinsic alignments and understanding how their modeling can be degenerate and worrying about how this can bias our cosmological parameters, the recent paper with myself, Marcus Rao, and again, Rachel Mandelbaum, looking into that. Feel free to chat to me about that later. And I think we're just about at the end. So I hope this has been sort of a whirlwind tour of, weak lensing at the beginning and then upcoming surveys and then a little bit of a deep dive into what we might be working on to try and mitigate the intrinsic alignment systematic effect. Obviously, there's a lot more going on, especially as Florent said in DESC, specifically with respect to baryons. I didn't get a chance to talk too much about galaxy bias, and photometric redshifts is a huge area of research in terms of needing to make sure that we really get that right to be able to trust our cosmology. So I think I will just end there, and I think Florent will tell us if we have time for questions or not.
Thank you very much, Danielle. Yes, sure. We do have time for a few questions. Let's start with questions in the room, maybe. I see one here, and then we'll take questions on Zoom as well.
Hello, thank you very much for the talk. I wonder if you have tried to use multi-wavelengths data. For instance, if you can model the foreground lens using X-ray, then you can estimate the background galaxy, how much it was modified because of the lensing, and estimate somehow the intrinsic shape and orientation and so on.
Okay, right. So I think that, right. So you're talking about modeling the lens on an individual basis, right? Okay. So kind of similar to a strong lensing approach, I guess. So in strong lensing, which is the case where you would actually be able to make a significant detection of this on a individual system basis, I think that would be that is something that is done. I believe it's not my area of expertise, but I believe multi-wavelength data would be very useful there. So this makes sense to me. And so in that case, I guess what you're doing is you are modeling the lens very carefully. I don't know, this may be your area of expertise, so please tell me if...
I don't do any of this.
Okay.
Okay. I think, but it is something that came to me that you can use this type of multiple approach to estimating really how much we have.
Yeah. So I think it's interesting because for weak lensing, we are really talking about, hundreds of millions of sources. And for lenses, it's, tens of millions or more. And so it would not be feasible for us to model the individual systems on a detailed basis. I think what's also interesting is because of the fact that we are really we are not, because we are measuring like a sort of general correlation function that's capturing the information for a sample, I don't think we necessarily always are able to discern the structures that are causing the lensing. So I think perhaps you could theoretically, but the volume of the sample is so large that I don't think it would be feasible. However, I think what you're suggesting using multi-wavelength data is something that's quite interesting for the intrinsic alignment method that I was just mentioning with different shape estimations, because you could imagine that even if you had even different bands and you measured the shape in different bands, you might get the same effect that you're describing, where you would have different, so you would have different sensitivities to different parts of the galaxy light profile in different bands. So that could be useful there. So yeah, it's an interesting idea.
Hey, Danielle, thanks for the talk. The shear estimator idea is very interesting, but are there signal to noise constraints that you have to take into account when choosing different radii to estimate the shear?
Yeah.
Like I assume on the outskirts, it's going to be super noisy, but on the interior, you're not going to have a lot of pixels.
Absolutely. Yes. Very good question. So yes. So this is something that we're trying to figure out with these simulations. So you're absolutely right that you will reach a limit on the interior where you don't have enough pixels, or even you will reach a limit where the PSF is the point spread function is the dominant effect. So yes, and on the outskirts, yeah, you obviously can't go too far or you won't have any signal. So we think that it will not be impossible, but this is something that we're exploring in the simulation phase. Yeah.
Nice talk, thank you.
Thanks.
I thought at the beginning you would do everything in French, but that's all right. At some point, so you show the part of Giorgio, I don't remember his
Yeah, yeah, Christos, yeah.
So would you think like the alignment differ as a function of radius? Do you think with a model we don't really care and we will fit some kind of effective intrinsic alignment and that won't impact any cosmological analysis at the end?
So you're saying like if we pick a radius to measure at, and then it doesn't really matter because you just fit some, yeah. So I think that's basically what we're doing at the moment, right? We get some amplitude and it doesn't super matter because, okay, it's to do with the shape. It's all sort of self-consistently internal, right? But it does raise a question of, do we need to worry about if we're trying to make, if we were ever trying to say, use priors from one survey that use one shape estimator for another survey, if it was ever tight enough in the measurements that you would be within this kind of a scale, then we have to worry about the fact that there's different shape estimators, I think. But yeah, I think at the moment we're doing what you're saying. We're just saying it's an effective number that is just tied to the shape estimator being used.
And regardless what Nick did, we don't really, in hydrodynamical simulations, did we see this effect as well of alignment?
Yeah.
With radius?
Yeah, we do. Yeah. There's some from like Tenetti et al. And I'd have to check the other papers, but yeah, I can send you some stuff if you're interested. Yeah.
Thank you.
Yeah.
Any more question? There's one here. Quick question, Pete.
Quick then. Thanks for the talk first. And can you say some more word about the essay tension, because you motivated a bit, but I didn't quite understand how it impacts all of those things.
Yeah, sorry. I did just kind of stop talking about that. So I guess the reason the essay tension was something I started with was because we we do, yeah, so we see, so I guess I'll just say generally, like we see this difference in the measured value of S8, which is sigma 8 times the square root of omega m over 0.3, or it's a combination of S8 and omega m. And we see a difference depending on the type of observable at a level of like 2 to 3 sigma currently. I guess the reason it's related to what I was talking about later is because we have currently, I think people are unsure if this is potentially due to a systematic effect in either the cosmic microwave background analysis or the late time analysis. So weak lensing, galaxy clustering. So theoretically, if you have the wrong modeling of intrinsic alignment, for example, or some weird combination of the wrong modelings for intrinsic alignment, photometric redshifts, baryons, whatever, you could be getting a bias in sigma 8 that is due to that and not due to physics. I did kind of, it was maybe a bit cheeky to put it in as a motivation. I think it's good context, but I don't think that intrinsic alignments are the cause. Personally, I don't think that could be independently the cause of the S8 tension. Could it be some combination of weird modeling biases? It could. But I think if I was gonna pick one of the astrophysical systematic that could be potentially the result of this, like people have definitely suggested baryons are more likely to be possible to be that. Then I don't think intrinsic alignments is probably independently possible to cause it.
Yeah. Thank you for a presentation. Quick clarification. Towards the end, you made the claim that alignments within dark halos, so in the HOD model, are not sufficient to explain what is observed. Is that correct? Or
so specifically for satellite galaxy alignments with central galaxies, so both their own central galaxy. So if we just consider the satellite galaxy alignment with respect to, so basically, okay, so yeah, the model that is being used to populate the simulation only cares about the satellite galaxy being aligned with the central in its own halo or with the center of the halo. That is being proposed here has no information about the outside. What we see is that when we use that model to populate a simulation, we cannot replicate the central satellite 2-point function as we see it in hydrodynamical simulations. Mm-hmm. So what I was suggesting is that this seems to indicate that there is an effect of the satellite alignment that is not just within the halo, but it's speculative. Yeah.
Right. I think it is time to close this session so we can thank our speaker again and have a good afternoon.